quick overview. We talked about the atom and the electrons. They get excited and they move out from their ground state, and when they move back down to their ground state, they release a photon of light. Depending on how far they move will depend on how much energy they have. The shorter the wavelength, the higher the energy. Since that electron transitioned more levels, it has higher energy. This second electron only transitioned one level, so it absorbed less energy, so it was able to release less energy, which has a longer wavelength. This would be red, and this would be violet. Then we did calculations. So, violet light has a wavelength of 410 nanometers. The speed of light, 2.998 times 10 to the 8th meters per second equals wavelength times frequency. So, 2.998 times 10 to the 8th meters per second equals 4.10 times 10 to the negative 7th meters times frequency. I needed to convert my nanometers to meters. 1 times 10 to the 9th nanometers equals 1 meter. So then I'm solving for frequency, which means I'm getting it by itself. So I divide both sides by wavelength, 4.10 times 10 to the negative 7th meters. Those become 1. My meters cancel. And my frequency equals 7.31 times 10 to the 14th seconds to the negative 1. Now that I have frequency, I can find energy. Energy equals Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, times frequency, 7.31 times 10 to the 14th seconds to the negative 1. So my energy equals 4.85 times 10 to the negative 19th. The seconds cancel, so I'm left with the joules. That's joules per 1 photon. So 1 electron moving, 1 wavelength of light. We don't ever work in 1 photon, we work in a mole. So 1 mole equals 6.022 times 10 to the 23rd photons. So I need to multiply my energy times 6.022 times 10 to the 23rd. And I get my energy to be 291769.54 joules per mole. Just to make it difficult, we need to put that in kilojoules per mole. So it's 292 kilojoules per